Hello everyone, I'm Yufengzhou Ai, and my topic is optimization in communication network design. Yes, in the network design, our main purpose is to achieve ultimate network performance. So, what is the network performance? Just imagine that you work in a company and every day there are so many people calling to your company and to get some information details so that you if you work for the technique department you will want to know that how many phone calls can our company's network stand, so how many phone calls can we make most in one day. So this is the purpose, and then we raise the question so that we want to how to realize it, what kind of problem it is. Apparently, it's the objective function is a nonlinear objective function, and the constraints are also nonlinear constraints. So it turns out to be a nonlinear programming. So how to solve this problem? Our first thought is to apply the Lagrange multiplier and the Lagrange augment function, because there are several advantages of this kind of method. There are two main pros of this Lagrange method. The first one is it's clear mathematical theory. So why the mathematics theory is clear? Because we can simply use the Taylor expansion. So this is and plus the minus, so we just ignore them. So this is the function, and this is the first order condition. If the first order condition equals 0, so if apparently this part is greater than 0, so if this part is greater than 0, so we can make sure we can confirm that this one is its local minimum, and if this second order condition is less than 0, so this part must be the local maximum. So that this is the mathematical theory of the Lagrange method. So it seems to be simple, and it is easy to generate a formula. So let's assume that our objective function is max fx, and the constraints are c equals f1 of x. So the Lagrange function should be L equals f of x plus. So this is its Lagrange augment function, and how to solve it? We can introduce KKT problems, KKT conditions. So the first order condition of L equals 0, and this part equals 0. Since it's equality constraint, so there's no requirement on lambda, so lambda is free. So that's the how we generate the formula. So it looks simple, but can we just directly use the Lagrange method? Of course we can, but there are some cons to directly use this kind of method. The first one is no or lack of convergence. The second one is fraught with assignation. Third one is tune parameters may affect the outcomes. So that this method is not very good or not perfect. So what method should we use? So we proposed a heuristic modification to the search algorithm. So what's the advantage of this kind of algorithm? It's a fine tuning of the parameters was used. The resulting or indicative of convergence to the optimal solution at reasonable speed so that it can reach the optimal solution, reach the convergence more quickly, and we can get a more accurate optimal solution. That's it. They are its advantage. So the projection heuristic is based on the use of projection of the gradients on an appropriate plane determined by the constraint surface. This is its theory or algorithm. And then if there's an improvement for our first trial, so that we can go to the next iteration until there's no improvement on that step. So if we reach that step, we just finish our work because we've already reached our optimal solutions. So here is optimization problems. Our purpose is find the maximum of S of lambda. So what is the S of lambda in our networking problems? S of lambda is the total throughput. That is the performance measure. The sum of throughput on every circuit. Every circuit is from circuit 1 to circuit J, and Pj of lambda is the probability that an incoming call, the probability that the call may cause in this circuit J. That is the definition of the objective function and the constraints. So because our method is based on Lagrange method, so we should apply our typical Lagrange augment function. Since in this problem lambda is the input vector, so we should take derivative against lambda on both sides of the equation. This is our first order condition, and we reintroduce the Lagrange multiplier. So this one I miswriting it. It should be eta, not the lambda. So the second, because the former equation is Lagrange function, this is a Lagrange function, the first order condition, so that we should improve it. So how can we improve it? Our ultimate goal is to achieve optimal network performance, which depends on a large of factors, some traffic, some node body routing, or some admission control. Here we approach this problem by exercising an admission control policy on course under the assumption that routers and offered nodes on each of the circuits were fixed. So it's not time varying, it's fixed. It's in this node we again face the roads, but instead of determining the best admission control policy for fixed offer node, we determine the offer node that maximize the throughput for fixed admission control policy. And then we assume the statistical base the portion distribution, so the income call at the time is followed portion distribution. It's very common in our probability classes. So I think it's a reasonable assumption. And xj is the number of calls can be admitted by a single circuit. uj is the service rate of that circuit. So we can get the partial pj of lambda, partial lambda I is equals to this one. So we can plug this one into our former first order condition equation. So we would like to guide the search in a direction of increasing throughput so that it tries to proceed parallel to the curator at which the blocking probability is at the specific quality of service value. This considers that exactly one blocking probability is located within the eta of the quality of service for exactly one value of j. So we'll introduce the vector d, which equals to the component of gradient of throughput, the gradient of s orthogonal to the gradient of blocking probability, which is to say d equals this part. And finally, we insert d into the former Lagrange objective function to replace partial s partial lambda I. That is to replace this part. And then we can get the upgraded function, and that is our ultimate function. So how does this upgraded function works? In this case, we assume ti equals 6, xj equals 4, and qj equals 0.3. And we can get two figures. The first figure is we use the basic search techniques, and the second one is we use our upgraded search techniques. So we can see that after 200, after 200 iterations, these two figures are very similar. So they are quite similar, right? But the first 100 iterations, it shows that now the older ones are very the points are dotted everywhere, right? It's not very, we cannot find patterns on the first 100 search. But in this one, with the revised algorithm, we can know that the search in the line is very good. It seems to be follow a certain of patterns, so that in the beginning of trials, there's a lot of improvement in our second method. So that the advantage of the projection algorithm is that first is established a capacity-like result for a given network in which the roads are fixed. In other words, even though the network operator normally will not choose the input node vector, it will be possible to predetermine what the ultimate capabilities of the network are for the chosen set of roads. That is, it will permit the network operator to slice the network and thus enrich the control capabilities in its operation. And the second advantage is that, for example, finding the best roads for a given input node, although a typical network operation problems is essentially unsolvable. It's quite difficult to solve this kind of problem, but we can we can find a convincible method to get closer to our optimal solutions. These are the two main advantages for this kind of search techniques, which is more powerful than our older methods. So that is all of my presentations. Thank you.